Here we're discussing Boyle's law as it pertains to the respiratory system and ventilation. So we have Boyle's law, which states basically to the effect that you have a volume times a pressure, and if you change one of those two things, the other will change. So if you change the volume, that will then change the pressure, and vice versa. As it pertains to ventilation, bringing air into and out of your lungs, we only have the ability to change the volume. We do not have the ability to change pressure. So ventilation is driven by changing the volume of our thoracic cavity. And this is important to remember because we cannot change the pressure of the atmosphere. We do not have that power. And we can't change the pressure in our intra-alveolar space. So we have to rely on changing volume in order to change pressure. And this is important when you're trying to understand airflow. So airflow is a rate. It's always going to be a volume per time. And so this volume is determined by changing the volume of our thoracic cavity. And that in turn changes the pressure in the intraalveolar space with respect to atmospheric pressure, setting up a pressure gradient. And as things move from high to low, you're trying to make the intraalveolar pressure lower than atmosphere to bring air in, and then making the intraalveolar pressure greater than atmosphere to drive air out. And so this is what is referred to as the pressure difference. This is going to be divided by the resistance of the bronchi. Resistance is something that the airflow is going to have to overcome. And so as resistance goes up in situations like bronchoconstriction, as asthma, anaphylactic shock, some type of immune or allergic reaction, anything that can increase resistance is going to decrease airflow if you don't have a concomitant increase in the delta P, or difference in pressure between intraalveolar pressure and atmospheric pressure. So, so real quick, this graph right here is referring to airflow, and it's going to be in relation to atmospheric pressure. So the pressure in the alveoli, intraalveolar pressure here, is going to start at 0 millimeters of mercury of pressure. And this is normal tidal breathing, tidal breath. And as the thoracic volume increases, so this would be P1, as we increase the volume of the thoracic cavity, this is going to expand. So this is increasing the volume of the lungs or the thoracic cavity, and that in turn is going to cause a decrease in the pressure in the alveoli, alveolar pressure, because as it expands out, the molecules have a bigger volume, and so they can spread out, and that will actually decrease the pressure. So P2, so this would be V2, is going to end up being 1 millimeter of mercury less than atmosphere. And so you get this negative 1 millimeter mercury pressure because it is 1 millimeter mercury less than atmospheric pressure. So by changing the volume of your thoracic cage or cavity, you are decreasing the pressure in the alveoli. Now you have a pressure gradient, a delta P of 1 millimeter of mercury. And that's enough to drive in 500 mLs of air. That's your flow right there. Then once you reach equilibrium, so it's going to be 0 again because you have air coming in down its pressure gradient, right? So atmosphere is high and it's going into the alveoli. so it reaches 0, you release the diaphragm. And when you stop contracting your diaphragm, that will decrease the thoracic volume. So now you have a new volume, which is essentially the volume you started with. And that will actually drive the pressure up, because now you're constricting and pushing those molecules closer together. That increases the pressure, and you're going to end up with a alveolar pressure that is actually greater. So that's a +1, greater than atmospheric pressure. And that creates a pressure gradient, because now P alveoli is greater than the pressure in the atmosphere by 1 millimeter mercury, and that will propel the air to flow out until you're back to 0 or equilibrium, and you would start the process over, right? So you're moving again, another 500 mLs out here, and that will flow out. So you're moving about 500 mLs of air into and out of your lungs with every tidal breath. And this is done again due to changing the volume of the thoracic cavity. And by doing that, you then change intraalveolar pressure as it relates to atmospheric pressure. And that is how Boyle's law drives ventilation.